Hello, my name is Jeremiah, and this is my physics lab report number 2 for Intro to Physics 2211 at Georgia Tech. Let's take a glance at the topics that are going to be covered in this lab report. We'll start out with an introduction to the lab. I'll explain the different physics fundamentals needed for this lab. I'll dive deeper into the process of the experiment and the coding, and then I'll explain what you just saw in the conclusion. It's time to begin with the introduction to the experiment. The purpose of this experiment is to show Newton's second law of motion by observing a system in a normal setting, meaning the net force is non-zero. The forces present in this experiment are gravity and drag. Terminal velocity will also be briefly discussed, and it is reached simply when the force of gravity is equal to the force of drag. Now that we know the basis of our experiment, let's get into the physics laws and forces that are at play here. The first fundamental is Newton's second law of motion, which states the acceleration of an object is dependent on the object's mass and the net force acting on the object. In this experiment, the net force or acceleration is non-zero, so the velocity update equation, v final equals v initial plus f net over m times delta t, will not state the initial velocity is the same as the final velocity. The next fundamental is the force of gravity, which acts in the negative y direction. The equation is the force of gravity equals negative mg times j hat, in which m equals mass, g is equal to the gravitational constant for objects near the surface of the Earth, or 9.8, and j hat is equal to the unit vector of the force. The last fundamental is the force of drag, which acts in the direction opposite to the object's motion. The equation is the force of drag equals negative b times v squared times v hat, in which b is the proportionality constant, v is the velocity, and v hat is the unit vector, which cancels out the negative out front. We have discussed the background and explained the things that are going to happen in the experiment, so now we will move on to the experiment itself. First, I will describe how the experiment was set up. A sock with a length of 0.33 meters and a mass of 0.007 kilograms was dropped from the origin of a coordinate plane and moved in the negative y direction until reaching the ground. This video was then put into a software called Tracker and analyzed from when the sock center of mass entered the screen and was cut when it exited the screen. Finally, two computational models were made using GlowScript, one with just gravity and the other with gravity and drag. After this, the position and velocity graphs were compared in the y direction only. Here's the video of the sock and the position over time graph that corresponds with the y component. This is the GlowScript code for the computation model of the experiment when it's only affected by gravity. As you can see, since gravity is the only thing acting on the system, F net is going to be equal to the gravitational force equation for objects near Earth's surface. The velocity and position update formulas are written underneath so that we can measure changes in position and velocity of the models. The graph of the compared data shows the sock fell less rapidly than the object only affected by gravity. Now this is the GlowScript code for the computational model of the experiment when it's affected by gravity and drag. The only difference in the code is that there is a proportionality constant that must be updated, and F net is now equal to the force of drag added to the force of gravity. The graph of the compared data this time shows that the sock and the model that showed gravity and drag fell less rapidly than the model affected by just gravity. It is also evident that the position relative to time of the observed line and the line showing gravity and drag are very similar. Now that we have completed the experiment and organized the data, let's conclude by talking about what it all means. The computational model that contained just gravitational force was not as accurate of a predictor of the position of the sock as the model that contained gravitational and drag force. This is because there was gravity and drag acting on the sock in the video rather than just gravity. Unfortunately, neither simulation reached terminal velocity because the simulations were too short due to mimicking the conditions of the sock experiment. There were some possible places where errors could have been made in this lab. One of them is that the sock did not fall completely straight down, so there was some movement in the x direction even when the axis was rotated to try and mitigate this as much as possible. There were also likely some tracking errors made when manually tracking the center of mass of the sock because I had to eyeball it. You may be wondering what would happen to the velocity if the sock was thrown down. The answer is that the sock would reach terminal velocity quicker. On a graph, the line representing the velocity flattening out means that the terminal velocity has been reached. The second graph shows a velocity with a greater magnitude than the first, and the line flattens out just a tad bit quicker. Thank you.